All right, we're ready to get started now with Julian and Clemens with Movfuscator Be Gone.
Cool. All right, thank you. So, as many of you know, this is a follow-up talk on the Movfuscator talk done by Chris Thomas last year. So my first quick question would be, who attended that talk or saw it recorded online? Okay.
That's quite a good number.
Actually, quite a bit. Okay, so our subtitle is Recovering from Soul-Crushing RE Nightmares, which is quite a reference to last year's talk. And as you can see, this is progressive, so we're still work in progress software, writing a deobfuscator. And we would like to stress the fact that this is not a personal attack on Chris Thomas. And also, we would like to anticipate that our deobfuscator does resubstitution of those move instructions very carefully, I would say. All right, a little bit about us. So who are we actually? We are, well, mainly CTF players. We play for a team from Germany called Hackabschor, and we invest a lot of time into solving crazy exploitation, reverse engineering, and cryptography tasks. And whenever we are not playing CTF, then, well, I am trying to get a PhD in the field of program analysis, low-level program analysis and deobfuscation. And Clemens just finished his bachelor thesis. He also had the doubtful honor of writing the thesis on deobfuscation. So he probably now knows that move code very well and can elaborate on that a little bit later. Okay, to get us synced, I will try to cover the Movfuscator at a high level, such that you know how it works, or how it is made up internally. So the story of Movfuscation is probably like this. There is this strange discipline amongst computer scientists to find Turing completeness where you wouldn't expect it. And the original paper on this was by Stephen Dolan in 2013, where he summarized that even if you remove all instructions from the Intel x86 instruction set, but the move instruction, then you're still not losing Turing completeness, which is kind of surprising, I would say. And then 2 years later, Christopher Thomas came and implemented a compiler, actually, who actually did that. And that was released at REcon 2015 last year. And he did that in two ways. So he had one version that he called the Movfuscator 1, which translated from brainfuck to x86 move, which is not so surprising because, well, brainfuck is quite low level. But he also spent great amounts of time to write a C to x86 move compiler, which is basically implemented as a virtual machine, and we will cover some of the internal workings right now. So we have the two references there if you are interested to read up on that. So let's assume we have a program that looks like this. So 5 basic blocks that are luckily, happily jumping to each other, and basic block 3 assumes that there is a loop. And then what many of you might know from malware or from industry standard obfuscators is something like this, called control flow flattening, where the obfuscator inserts a dispatcher that actually then does the basic block scheduling for you. So the left-hand version clearly conceals how many possible paths are there through the program, and also you can't tell anymore what basic block is scheduled after what basic block. And Movfuscation now takes the exact opposite way and creates something like this. So instead of flattening it, it does something we call linearization, which just aligns all basic blocks into one linear block that loops infinitely. So how is that implemented internally? Well, there is that static initialization stub, which basically registers 2 signal handlers. One for sig-ill, which basically is a trick that the program is its own sig-ill handler. And that makes that basic block 4, in order to jump to basic block 0 in that image, does not have to trigger an explicit jump, but could instead just trigger a sig-ill. In Doma's case, it's a move of a segment register into a general purpose register, well, to start execution over again. And of course, those signals have to nest. And the other one is, of course, you don't want to lose your ability to talk to the operating system, which is why he registers another signal handler for zigzag fault, which basically jumps to a dispatcher, which then calls external library functions. So it does that by triggering segfaults. So in context of Movfuscation, dereferencing 0 means, well, do a library call. Okay, to best understand how this is possible at all, we have a, well, quite verbose high-level C program here, and I know that slides and code don't like each other very much, but what this program should do is it calculates the factorial of the number that is passed in argv1, and if you compiled that program, as printed on the left, you would get a control flow graph as depicted on the right. So how is that done? Well, one observation is that each instruction of each basic block obviously needs to be executed each time it is passed, right? So whenever that loop retriggers, we have to execute all instructions again. And the problem is that not all instructions should manipulate our state. So the main trick of Movfuscation is actually whenever you introduce a variable, you actually introduce two variables. So you introduce an array with two entries, and the first entry of that array is a discard location with trash data, and the second entry at index 1 is the real data you're interested in. And if you follow that idea, then you can program a program like you can see in that do-while loop from line 12 to 24, which basically, well, takes a state variable, a global state, and evaluates that state, whether it is, well, in our case, we have state 0 and state 1. And if it's true, then it does the assignment on the left-hand side, the I and 1, you can see in line 13, to the real data. And if it's not, then it's done, the assignment is done to the scratch data. And, well, if you apply that iteratively, then you get that program calculating the factorial. Quite interesting. And in context of Movfuscation, this means that whenever we talk about something prefixed cell, we mean actually an array holding two variables, and one of those variables is scratch data. So a basic block in Movfuscation is then always starting with a sequence that takes that target register, which basically is equivalent to the state, what we saw here. And checks whether, let's, for example, take a look at basic block 3, whether the current basic block is the basic block that should be executed. And if it is so, then that on variable is set to true. The transformed semantics of the basic block 3, now written in move code, are executed. And at the end of that basic block, there is the sequence that the basic block checks whether the next basic block should be basic block 3 or 4. Remember, basic block 3 was the one that looped in the beginning. And then execution goes on. Now, one thing to remark is that arithmetic, doing only move, is quite tricky. Thomas implemented this using lookup tables. So you can imagine doing arithmetic for each and every possible processor instruction can blow up the binary quite a bit. And if we look at some statistics here, for instance, on the right-hand side, we have vanilla compiled programs. And on the left-hand side, we see the Movfuscated versions. So we can see that program sizes increase dramatically by a factor of up to, well, 2,000 almost. So note that's kilobyte versus megabytes. And also execution times, because that loop has to be executed all over again, is of course also quite awful. So if you compare the SHA-2 example, which basically just hashed 10,000 bytes together, took almost, well, a factor of, what's that, 4,000 times longer than the original version. So our thought when we saw that it was, well, it's quite cool, but it's also very slow, right? So who would ever in any productive way use that obfuscation technique? Yeah, well, and of course we forgot about CTF organizers. So of course it didn't take long until, well, challenges appeared during CTFs, where people thought it was a nice idea to torture CTF participants and throw Movfuscated binaries at them. And at that point we said, okay, no, this has to change. And if we deal with that rightly. So there's two easy solutions that we explicitly rejected. Number one, the brainfuck Movfuscator, well, is easy because there is a one-to-one relationship from brainfuck instructions to emitted move instructions. You could just statically resubmit it, resubstitute it, and you're done. Same goes for the C version, but, and that's quite cool, the original implementation of the Movfuscator also has a hardening.py script lying next to it. And what it does is it well, prevents exactly doing those pattern-based or pattern matching-based approaches. So it does register renaming, it does instruction reordering, it shuffles quite some bits. So we can't do any pattern-based approach anymore, and we're really forced to look at the semantics. And how we do that is now covered by Clemens.
So first of all, when we designed the Movfuscator, we had to think about what were our goals, because analyzing the Movfuscator binary, as you saw, can be quite tricky, quite difficult, even especially if you have to take into account that the extra hardening gets applied. So you can't, like Julian just said, you can't statically translate it back. So we sat down and thought about what would be the main priority. And we came up with staring at a wall of instructions is really bad and annoying. And it would help a lot if we actually get the control flow back. And that was our main objective. Apart from that, we wanted to retrieve symbols like what table does what operation. So that if in the end you load it into IDA, you know exactly what's going on, even though you have quite an amount of instructions, so you can figure out what is happening. And as a third priority, or as least priority here, is replacing the lookups by its instructions, by x86 instructions. Yeah, so that were the goals. And to recover the control flow, we do it in 4 stages. And in every stage builds on top of the previous stage. So in every stage we acquire some knowledge we need in the next stage. And in the beginning we don't have any knowledge about the program, apart from that it's Movfuscated and that it contains the initialization. So we analyze the setup. After that we have not enough knowledge to retrieve all the labels. Then we can look where the jumps are and where are they leading. And from all this information, we can finally build the control flow graph again. And well, that was our main priority. So let's get right onto it. How do we analyze the setup? As Julian mentioned, the first initialization sets up 2 signal handlers to do external calls and also to loop around. And it set up the stack as well. And the interesting part is here marked as 1. It is part of the main loop actually, but it is also statically in the binary and also not prone to any hardening because it's emitted only once. And that's at the time where the object files will get linked together or right before that. So you won't see any hardening on this part. So parsing it is quite simple. And as you see, the on variable will be initialized here. In the first statement, as selector at place init will be set to 1, and init is a variable that is statically set to 1 in the image of the binary, and after that init is set to 0. That makes sure that this basic block will only be executed once in the beginning of when the binary is first started, and then it calls main and exits. It's just setting up the execution of the other basic blocks. So from here we know where is cell on, and also we know where is on because, well, if we have the selector, we have the on as well. Building on top of that, we now can recover the labels. To do this, we run over the entire binary and pass the instructions using a capstone. And when a label occurs, because the way jumps are, a move instruction itself cannot target the instruction pointer, so it needs those entry points into labels where the execution is set to on, and they look like the code here, the 2 lines. You have the cell on, which is set to 1 under a special condition, and we now have to evaluate the condition and find the label therefore. And on the right side, you have an example here. We are using lookup tables, and because it's a 32-bit binary, you can't have full 32-bit lookup tables, so it will be split into multiple lookup tables, which makes this operation quite a vast amount of move instructions, and we have to put them together. That's the challenge here. And also in the beginning, we don't know what the lookup tables does. So instead of seeing the equals here and seeing the and here, you would just have addresses into tables. And now we have to beat the lookup tables. And what is the best way to beat lookup tables? Well, you just use lookup tables. This works for binary and Boolean. For binary operations, we access a specific element in the lookup table, which is distinct to this lookup table, so we make sure not 2 lookup tables have the same value there. And for Boolean operations, we calculate the score based on the results. For unary operations, we hash the tables, which works quite good. Yeah, now we have figured out what lookup table does fit to which address, and now we can translate back. And well, now we have here's the stream of instruction, which is exactly what I showed before. You can identify the equality lookups and the and. Not? Well, I guess so.
Well.
And the worst part is we still have to teach our computer how to work all the instructions together. So what we do is we start at the end. We know that when we assign 1 to cell on, that the result A is some kind of condition, and we start there. We do a taint analysis going backwards. We at first taint A, and the way taint propagates to move code backwards is quite obvious and quite easy to implement. So it works really, really well. And we can generate a graph out of it. And this looks way more handleable. I think you agree. And now from this graph, we still have a graph, and we still have to handle it somehow. So what we're doing next is we take this graph and translate it into an expression and feed it into an automatic theorem prover, namely set3. And this automatic theorem prover will look at it, and we ask, well, what value does target have to take so that A evaluates to 1? So under which condition will cell on be set to 1? And it will output us a constant function, which is just equal the label. So we then have the label, and we just remember where the label was and what's the label. So the virtual address and, well, the label. And this brings me to the third point. We have to identify jump targets. And all those instructions have in common that they access cell targets. So we do it very similar to the analyzation of the labels. We start from the selector of the target and see if it's toggled under some condition, like you see in the conditional jump. All the others have no condition, because jumps will always be executed, returns will always be executed, indirect jumps will always be executed. And then we also have to acquire the label, which we find in the subsequent instruction. or it could be something more complex, like in the indirect or return case. And it's not easy to distinguish those two cases, but with attained analysis of X, you end up either with a very simple case where just the stack gets dereferenced, or you have something way more complex, and the complex case is the indirect jump. The stack is obviously the return. And we then remember the position of the jump and where it leads us. This gives us a bunch of data. First, we just have those labels and the jumps on the left side, A, B, C, D, E, F. Then we connect them in a meaningful way, such that a label will just execute to the next block. And then we simplify the graph, and we get a control flow graph on the right. And that's all we need to do to recover the control flow graph.
Yeah, right. But so what? I mean, you don't remove all the moves. That might be the biggest concern right now.
Yeah, but it has the advantage that it can still handle hardened executables. We are doing a attained analysis, so it doesn't matter how the registers are named. It doesn't matter in which order they appear, because, well, it doesn't matter to the attained analysis. The data get propagated equally. Also, we get the control flow graph, which is a major help in reversing the binary in the end. We also, what I didn't cover is we generate a patched binary, which we then can execute, or which makes it, looking at it in IDA or something else, way more pleasant. We generate IDA symbols because, well, going all the way, recovering the labels and the targets, we go over all the tables, and so on the way we just generate those symbols, and we break them. We get them into a form that IDA can understand. So if you load it in the end, the patch binary with the symbols into IDA, you have quite a different experience than looking at the Movfuscator binary.
Right, and last but not least, we're using all those fancy new frameworks. So if Mr. Jensen is sitting in the audience, I don't know, the creator of Capstone and Keystone. So thanks a lot. That really helped in creating the Movfuscator. And also thanks fly out to Microsoft for creating a set 3 automatic theorem prover. And we actually had a demo.
We had a small demo.
But due to ongoing problems and due to the fact that everybody wants to go to the coffee break, I'm just quickly covering what the idea and the takeaways of that demo were. So we have this simple crack me, and I'm sure that most of you will almost instantly be able to tell what the needed input should be for the fgets in line 10 in order to get the smiley face, and not the sad one. But what we would have done is then we Movfuscate this, and then we throw this into the demofuscator. And then to prove our point, we would have taken this fancy new Anger binary analysis platform framework. And the cool thing is that Anger comes with a symbolic execution engine that actually works for low-level programs. And what you can then do is you can say, okay, whatever the fgets returns is symbolic data, so treat it as a formula. Then execute the full program from line 10 to line 16. Apply all those transformations to the formula, and then constrain res, the result variable, to be 0. And from that, you can feed it again into a theorem prover, and you will get actually the correct solution. And I know this is pretty lame that we can't show that live right now. So all I can offer is, well, I have it there on my notebook, but unfortunately not on this one.
Yeah, just come to us. And
if you're really interested in this, we just invite you, please come to us after the talk, and we will show you that it actually works after demofuscating it. And one of the takeaways also is that demofuscation takes, well, less than a second. So it's almost as fast as obfuscating it. So to conclude, this is the way you can reach us, our email addresses, also our PGP fingerprints, and of course we are open sourcing everything. So the source code of the Movfuscator, which is by the way about 4K lines of code, so there's many things we couldn't cover. Also, well, a summary of the Movfuscator, and if somebody wants to torture himself even more, then there's Clemens' bachelor thesis that you might read with, well, which might be quite a moving experience on 60 pages. And that's all we got for now.
Yeah, it covers the basics of the Movfuscation more in depth, and of the Movfuscation as well. So it might be interesting to read, but it isn't necessary. This presentation went over much.
Shut up, we're at that point. All right,
Okay.
Thank you very much.